Hey, good morning, everyone. Welcome to Thursday, where we are talking about geometric sequences, right? So, yesterday was all about arithmetic sequences and how they are a type of linear function. And a lot of you guys wrote on the Desmos activity that one of the things that distinguishes an arithmetic sequence from linear function is actually that it's a type of linear function, but it's always discrete. Okay. And in the same way, a geometric sequence is always discrete also, because just like arithmetic, we're talking about term numbers, right? The domain, the x values, I'm talking about my first term. If you've got a little one here, is 2. My second term is 4. My third term is 8, and so on. If you get an n here, that just means any term in the sequence, right? It could be the first, it could be the 100th. I don't know yet. There's a variable there. Okay, so because I can't have term like 1.25, right, this domain is always going to be a natural number or sometimes 0. We'll go through examples of that. But mostly it's just natural numbers 1, 2, 3, 4, 5. And because that domain is natural numbers, I'm not going to have any line in the middle of this connecting them. All right, so that's one thing to note. So another is that even though these are discrete, like what we worked with yesterday, it's not in a straight line. Okay. It's got like a little curve. If I were to connect it, right, it would have a little curve kind of going up. So, in the same way that arithmetic sequences are part of the linear function family, geometric sequences are part of what we call the exponential function family. All right. And if you remember with exponential functions, and again, same with geometric sequences, we are repeatedly multiplying. And this repeated multiplication is what we call a common ratio. So in this example, the common ratio, the R value, would be equal to 2. All right. And one way you can get it is just by looking and saying, oh, 2 times 2 is 4, times 2 is 8, times 2 is 16. But if you wanted to calculate it, you can always take any of the terms, like 16, and divide it or make a ratio with the term that comes before it. So 16 divided by 8 is 2, and that is your common ratio. All right. And they call it a common ratio because we made that fraction. You can make a fraction there, and that's your ratio. All right. So let's go on to the next slide. Oops. All right. Let me erase this. Okay. So the next slide, we are going to be doing an example. Excuse me. All right. So how many bacteria will there be? Let's see if I can make myself smaller. At 5 minutes, okay, and at 10 minutes. So at the very beginning of this, right, and let's kind of make a little table to the side here. Okay, so I'm saying my X and my Y. Okay, so remember the X value, it's always those natural numbers, and it is the first term, second term, third term. Okay, in this particular case, they say at the beginning. They don't start the first term until 1 minute. So here, this is one of the few examples where X can actually include 0. Okay, so I've got my first term, my second term, my third term, and here they're talking about minutes, right? My fourth term and my fifth term. Okay. All right. And we're talking about bacteria here. I wonder actually if this is one of the few cases where it might not be discrete, right? Because there might be a minute and a half, right? So let's just think about that. That's really interesting, right? Okay, so at the beginning, I've got 3 points, and I'm not just trying to write down the number of points. I'm also just trying, or the number of bacteria, right? If we're talking about the story, I'm also trying to figure out, okay, how is this growing? Okay. So the cool thing about these drawings is different people do see them in different ways. So I'm going to just share how I see it. All right. So how I see it is I see the same thing is happening 3 times for all of these. 2, 2, 2, 4, 4, 4, and then what is this? 4, and then so 8, 8, 8. Okay. So I see one dot happening 3 times. Okay, so I'm kind of looking here and then I'm multiplying by 3. So this one dot becomes 2 dots, and 2 times 3 gives me 6. Now this 2 dots or 2 bacteria become 4 bacteria. 4 times 3 gives me 12. 4 dots becomes 2, 4, 6, 8 dots. 8 times 3 becomes 24. Okay. And here I've got a cluster of 4, 8, 12, 16. So here I've got 16, and 16 times 3, I might actually have to do that. Well, let me see. 15 times 3, 15, 30, 45, and then 46, 47, 48, 3 more, so 48. Okay, so that's how I'm seeing them grow. Now I'm going to look here. What is the common ratio? So 3 times 2. Let's see if that holds. Okay. 6 times 2. Okay, it looks like this does hold, right? So where my common ratio here looks like it's going to be 2, right? So this would be A sub 0 because it's 0 minutes. A sub 1, just so that we're practicing our notation. This is the 2nd minute. This is the 3rd minute. Okay, and this is the 4th minute. Okay, so yeah, so I have times 2 times 2 times 2. All right, so 48 times 2. So 8 times 2 is 16. Carry the 1. And then 2 times 4 is 8, plus the 1 is 96. So at 5 minutes, there should be 96 bacteria, right, at 5 minutes. Okay, now I don't want this video to go as long as yesterday, so I'm going to let you guys figure out what it is at 10 minutes. So I'm just going to give you the hint that you're going to keep multiplying by 2, okay? All right. So again, yesterday, the arithmetic sequence has a common difference. If I'm talking about geometric, which is a type of exponential function, that has a common ratio. All right. So let's erase all of this. And while I'm doing that, maybe you guys can be thinking about what is the number of bacteria that would be had after 10 minutes. Okay. All right. I wish that this was like Zoom, where you can just click one button and all of your writing magically goes away. But here, we need to do it by hand. Okay. So let's just go to the next slide, and I'll continue erasing there, but at least you can see it. Okay, so here is the next problem. And as I continue erasing, I want you guys to think about a ball being dropped from a height, right? In this case, it's 500 meters, right? But just think of a ball. What happens to a ball when you drop it on the ground? And think of a bouncy ball, right? Don't just think of like I don't know, a ball that just thuds, right? Okay, so I'm thinking of that in my head. And I see that a ball is dropped from 500 meters. So if this is 500 meters, 500, this is where I drop the ball, right? And so I'm thinking of the ball going down, and then it goes like this, right? It's a bouncy ball. and then it goes a little bit lower until it eventually just like kind of stops. Okay. All right. So here at bounce 0, that would be at 500. Okay. So now what is the common ratio? Now here, 500 times what gives me 400? I don't know, right? 400 times what gives me 320, right? 320 times what gives me 256. So do you guys have any idea how I might find that? Okay. So remember back to 2 slides ago where I can take any of these terms, right? Let me just take 320. Why not? Okay. And I'm going to divide it by the number before it. So I'm going to divide it by 400. Okay, so let's see. I'm just going to do that in my calculator, and I should get 0.8. Now, you could also write that as 8/10. Okay, and if I divide 8 by 2, that gives me 4. I'm just reducing that. And 10 divided by 2 gives me 5. Okay, so these are all equivalent. I would probably either choose the simplest version or the most reduced version of the fraction or this decimal. So again, I'm never going to put divide by, but I am going to put times maybe a fraction like in this case. Okay, all right, so the common ratio is either 4/5, 0.8. If you put either of these two, it's not how it's most likely written, right? We expect you to either do a reduced version of a fraction if you do that. But any of these 4, 1, 2, 3, 4 are equivalent and would be accurate. Okay, so how high would that fourth bounce be? And so I am actually going to do that here. All right, so we have the fourth bounce, and 256 times 4/5 or 0.8. Okay, and I have, all right. So in my calculator on my phone, I am doing 256 times, and I get 204.8. Okay, so about 205 meters. All right, that's how high the fourth bounce would be. Okay, remember the y values, the range can be decimals. It's just the domain that we normally say, term 1, term 2, term 3. Okay, that's it for today, and good luck in the Desmos. I will see you guys later.